Well, we'll get into exponential functions. So let's review our rules. So here's our first one. If we have a to the s times a to the t, right, we're adding a to the s plus t. That's the product of exponentials. The quotient property of exponents is the next one, a to the s over a to the t, a to the s minus t. And here's some examples over here, of course. 2 to the 6 over 2 to the third leaves us with 3 2's on the top, right? The third one is the power of a power property for exponentials. So like 2 to the third to the fifth is 2 to the 15th because you have 5 sets of 2 to the third. The fourth one there is the power of a product. It's called power of a product. So a to the a times b to the s. You got to take each of those to that power, right? So 2 times 3 to the fifth is the same as 2 to the fifth times 3 to the fifth, or 6 to the fifth, right? It's all the same thing. Anything to the s power is still going to be 1. It's like 1 to the 34th. Anything to the 0 power would be 1, right? A negative exponent rule, a to the negative s is 1 over a to the s. Like 4 to the negative 2 would be 1 over 4 squared. And finally, one way to deal with a quotient negative taken to a negative exponent is to flip that over and make it positive, right? So there's two ways to do that. So you have 2/3 to the negative 2. You can write that as 3/2 to the 2. Or if you want, you can also go 2 to the negative 2 and 3 to the negative 2, which would be that one goes up, becomes 3 squared. The 2 to the negative 2 goes down, becomes 2 squared, right? They're both the same thing. All right, let's go ahead and do some calculator approximation. Let's just make sure we can punch in 5 to an irrational number. So 5 to the square root of 3. So if you want to pull up Desmos, and let's pull up our scientific calculator in Desmos. And 5, and now I use the shift 6, but you can also, if you want, use that a to the b right there, and that'll take you to the square root of 3. So now I'm going to go square root 3. And so we get 16.24245. I think it was 08 something. I don't know. Anyways, let's round it to 3 decimal places. So to the thousandths position. So since that's a 4 to the right of that, we'll just leave it at 16.242. And let's also go e to the 1.6. We're actually going to define e later in the course, but e is another very famous irrational number like pi. E is approximately 2.718. Again, we'll do that definition of it later, but let's just make sure right now we can use e. So you can just use the letter e, and notice it's right now it's giving you what e is. And by the way, this keeps going. It's an irrational number, but we're going to take it to the, so I can either do shift 6 or hit that a to the b, 1.6, and there it is, 4.95303. And we'll round this to 2 decimal places, so the 100th position. So that 3 will leave that the same. Let's take a look at a function, an exponential function, and to kind of look at its characteristics. So we'll make a table of values, and let's let b be 2. So 2. Let's plot 2 to the x. So for example, if x is negative 2, we would have y being 2 to the negative 2. Well, that's 1 over 2 squared, or 1/4, right? So the point is -2, 1/4. So -2, and I'm up 1/4 of the way. Let's do -1. So 2 to the -1 would be 1/2 to the 1, which is 1/2. So when I plugged in -1, I got 1/2. Let's do 2 to the 0. Anything to the 0 is 1. So when I plug in 0, I get 1. 0, 1. -1, 1/2. I should have put that on there. I put that one on there now. Let's go plug 1 in. So 2 to the 1, which is 2. So I plug 1 in, I get 2. Let's plug 2 in. 2 squared is 4. So I plug 2 in, I get 4. Let's do some more here. 3. I get 2 to the 3rd, which is 8. So 3, oops. When I plug 3 in, I get 8. When I plug 4 in, I get 16, so on. Let me also do -3. If I go -3, 2 to the -3 is 1/2 to the 3rd, 1/8. And I could keep going with that as well to the left. And let's plot all these points here. So I've already plotted 0, 1. Let me go 1, 2. Let me go 2, 4, 3, 8. And I don't really have room for 4, 16, so I'll stop there. But I did do -2, 4. Let's go -3. I'm only 1/8 of the way up. -4, I'm only 1/16 of the way up. So you notice as I go to the left here, it's just getting closer and closer and closer to 0. Right? So in other words, because I'm getting closer and closer to 0, but I'm not touching it, what I have is a horizontal asymptote at y = 0. Okay? And then as I'm going to the right, let me follow it to the right and connect the dots. It's shooting up to infinity. Right? As x gets increasingly larger, y gets increasingly larger. But as x gets smaller, right, we pick values like -3, -4, -5, and so on. As I let those values approach negative infinity, the y value approaches 0. Right? So that's why we have that horizontal asymptote at y = 0. Right? Our domain here, notice I can pick anything. Domains, -infinity, +infinity. I can pick any x values I want. So -infinity, +infinity. So all real numbers. But the range, on the other hand, the lowest y value is 0. It doesn't quite hit it, and then it goes up to infinity, right? So it does not hit 0, but it goes up. So our range from 0, again, from 0 up, but I never touch a y value of 0. All right, let's do one now where the base is e. And remember, I said e. In fact, let me give you the definition. E is when x goes to infinity, it's 1 + 1/x to the x. Well, guess what? This is an irrational, 2.71828, blah, blah, blah. Anyways, it keeps going. So if you can kind of remember that e is 2.718, this is kind of like 2.718 to the x again. But you got to use e, okay? But that's the number. You want to remember that e is 2.718, okay? And let's go ahead and let's graph this one. So let's go e to the -2, and I would pull out my scientific calculator and punch that in. So y is e to the -2, or 1/e squared. So this is 1/2.718 squared. So let's punch that in. Let's get a value for that. So e to the -2, or if you want, you can also do 1 divided by e squared, right? Same thing, 0.135335. I'll go to 3 decimal places. So -2 gives me 0.135. Now let's plug in -1. So y would be e to the -1. So again, that's 1/2.718. So I punch that in, and that's approximately 0.368. So when I plug in -1, I get 0.368. Let's plug in 0, e to the 0. Anything to the 0 is 1. So when I plugged in 0, I get 1. Notice I have that same 0, comma 1. That's a big point on there, because anytime you have b to the x, our first base was 2 to the x. This one's e to the x. You're going to have a y-intercept of 0, comma 1. Okay, that's an important point when you're thinking about the transformations. Let's move on here to 1. So e to the 1, so that's approximately 2.718. So 0, comma 2.718. And then let's plug in e squared. Plug in e squared and I get, let's see, that would be 7.389. So 2, comma 7.389. And let's graph this one. So I already graphed that y-intercept 0, 1. Let's go -1, comma 0.368, so about right there. -2, but now I'm only up 0.135. I could plug in -3, it'd be even lower, so you probably notice it's going to 0 on the left. Let's go to the right now. 1, oops, that's supposed to be a 1 right there. 1, comma 2.718, about right there. 2, comma 7.389, about right there. So if you notice, it goes up a little quicker than that last one, but it still has a y-intercept, a horizontal asymptote of y being 0. And if you notice, the domain is still all reals, and the range is 0 to infinity. 0 up, right, would be our range. So the larger the number on the bottom, last time we had 2 to the x. This one I have 2.718 to the x. The larger the number is on the bottom, the steeper the graph is, right? As far as, so it's kind of like vertically stretching it out, right? It's a little steeper here. So what if we instead put a fraction in front then? What would that do to the graph, right? 1/2 to the x. Well, let's go ahead and plug some points in. Let's do our 0 first. So 1/2 to the 0. Well, anything to the 0 is 1. So I still have 0, comma 1 on the graph. Now let's go to the right first. So 1/2 to the 1. That's 1 to the 1 over 2 to the 1. So still 1/2. Plugged in 1, I got 1/2. Plugged in 1, I got 1/2. So it's going down. Plug in 2, 1/2 squared. So 1 squared over 2 squared. 2, comma 1/4. I could throw 3 in. I get 1/2 to the third, which is 1/8. Let's plug those 2, comma 4th, 3, comma 8. And we could keep going with that, and you're going to see it's going to taper off to the left. So it still has horizontal asymptote y equals 0. But this time it's decreasing as it goes to the right. Well, now let's go to the left. Let's plug in -1, 1/2 to the -1. So I got 1 to the -1 over 2 to the -1. So in other words, they just flip-flop. It'll be 2 to the 1 over 1 to the 1. So when I plug in -1, I get 2. When I plug in -2, so 1/2 to the -2, and let's do it with the property. That'd be 2 over 1 squared. 2 squared is 4. When I plug in -2, I get 4. Let's do one more, and I plug in -3. Y would be 1/2 to -3. That'd be 2 over 1 to the third. So when I plug in -3, I get 8. And look what happens if I plug in something for my base that's less than 1, like 1/2. See how it's a decreasing function this time. From left to right, it decreases exponentially. So our domain is still all reals. Our range is still 0 to infinity on this. All right, let's take a look at some transformations now. So 2 to the x and 2 to the x minus 4. So if you remember, the original 2 to the x is right here. So here's our parent function, right? So what would the minus 4 do? Well, we know that would just be a vertical shift down 4, right? And we know the original function had a y equals 0 horizontal asymptote. So if we bump that whole thing down 4 on the graph, it'll be y equals -4, and every other point, would be similar, right? Again, I'm not drawing this perfectly because I haven't plotted any points, but it would be that exact same graph down 4, right? And of course, again, you could plot some points if you weren't sure. Like, let's throw 0 in. 2 to the 0 is 1 minus 4, which is -3. So you have that point 0, -3 right there. Let's plug 1 in. 2 to the 1 is 2. 2 minus 4 is -2. So I got 1, -2 right there. Let's plug 2 in. 2 squared is 4. 4 minus 4 is 0. There's 2, 0, and so on, right? You could plot a bunch of points. But your domain here is still all real numbers. The horizontal asymptote dropped down 4. So instead of y equals 0, now it's y equals -4. And then the range is from -4 up. But again, you don't touch -4. All right, so change your range on that. So that's a shift down 4, 2 to the x minus 4. You could do a shift up 4 if you would have went +4, right, and so on. So, all right, let's do one. How about if we put a negative in front of the function? Again, here's our 2 to the x, which has a horizontal asymptote of y equals 0. And what would that negative in front do? Well, if you remember, when you put a negative in front, that's a reflection in front of the original function. That's a reflection about the x-axis. Okay, so you flip it about the x-axis. So you're still going to have y equals 0 as your horizontal asymptote, but all those points are going to be flip-flopped. So instead of 0, 1, I'm going to have 0, -1. Instead of 1, 2, I'm going to have 1, -2. Instead of 2, 4, I'm going to have 2, -4, and so on. And you could flip-flop all those points about the x-axis. And again, if in doubt, plug a few points in. Let's throw 0 in. -2 to the 0. Well, we know 2 to the 0 is 1, so I have -1. 0, -1. There it is. Let's throw in 1. -2 to the 1. Well, 2 to the 1 is 2, so I got -2. Throw 2 in. -2 squared, which is -4. And so on, right? There's that one. There's anyways. You could throw some more points in. You should see that thing reflecting about the horizontal asymptote. The domain is still -infinity to +infinity. The horizontal asymptote is still the same, still y equals 0. But the range is different. It comes from -infinity up to 0. Doesn't touch 0. So notice on this one here, we have 3 to the x plus 2 minus 2. So our parent function is actually 3 to the x on this. So 3 to the x has the point 0, 1, 1, 3, and so on, 2, 9, blah, blah, blah. And it still has that y equals 0, right? So it's a little steeper than the 2 to the x, but just note that, hey, this is 3 to the x, but what did we do to 3 to the x? Well, we're going to bump it down 2. So down 2. I'm going to take the whole thing down 2. So that automatically takes y equals 0 down to y equals -2. There's our new horizontal asymptote. And then what does this plus 2 do? Which direction is that? That's the one that takes us left 2. It's up there in the exponent. X is replaced with x plus 2. So it takes the whole thing left 2. Okay, so we're left 2 down 2. So I'm going to take that point 0, 1, and I'm going to go left 2 and down 2, and it's right there. I'm going to take the point 1, 3, left 2, down 2, right there. And I could plot a bunch of other points, but I'm good with that, at least as far as drawing this thing. The domain is still -infinity, +infinity. The range is now down 2, so from -2 up, right? And again, you could always plot some points, right? So Negative 2 is a good one because you'd have negative 2 plus 2 in the exponent. Well, 3 to the 0 is 1, and 1 minus 2 is negative 1. So negative 2, negative 1. That was that point right there that we already had, right? Negative 1 is another good one. Negative 1 plus 3 to the negative 1 plus 2 minus 2. That'd be 3 to the 1 minus 2, which is 1. So negative 1, comma 1. There's that point right there. And so on. You could plug some other points in if you choose to. So that's a horizontal shift left 2 and a vertical shift down 2. That's an example of that. Right? All right, this one. It looks like we have our base here is 1/3. So this is, well, actually, you could do this a couple different ways. I would personally start with 1/3 to the x, but you could also do 3 to the negative 1. Let me do it this way. 3 to the negative 1 is another way to do this. So you could start with 3 to the x and then think about it that way, right? And that's what I have here in the notes. So 3 to the x, which still has horizontal asymptote y equals 0, right? So let's do it that way first, and then maybe we'll do it with 1/3 to the x as the second approach, with being the parent function. Okay. Well, these are multiplied, so I got negative x minus 3. Okay. And so let's see what happens here. We're going to flip it. That'll be a reflection about the y-axis. So now we would be here in red. Okay. And then I would go right 3. I'm going to take that point 0, 1. I'm going to right 3. And now it'd be like the black one. And finally, I'm going to go up 1. And I would be the blue one there. Okay? And that would be our function, the one in blue. Okay? That's our baby, yes, that one. Okay. Now we bumped it up 1, so the horizontal asymptote will be y equals 0 on this. Okay, so horizontal. Oh, I'm sorry, bumped it up 1. Good grief. Y equals 1. So horizontal asymptote, bumped it up 1. Y equals 1. Okay, domain still negative infinity, positive infinity, but we bumped it up 1. So the range would go from 1 to infinity on that. Which the horizontal asymptote y equals 1, right? All right, what if I did this instead? So let me come back here. Let me erase this for just a sec. All right, so this time I'm going to have the parent function be 1/3 to the x. Okay, so it's not this picture. So 1/3 to the x, 1/3 to the 0 is 0, 1/3 to the 1 is 1 comma 1/3, 1/3 to the negative 1 is negative 1 comma 3. So here's 1/3 dx. That's the same as 3 to the negative x. Okay, so it's the same as 3 to the x reflected about the y-axis. It still has a horizontal asymptote of y equals 0. Okay, but I'm going to use this as my parent function this time, and then what I'm going to do is I'm going to move it right 3, and I'm going to move it up 1. So if I take that, and I'm going to take that point 0 comma 1, I'm going to go right 3 and up 1. There it is. I'm going to take the point negative 1, 3, negative 1, 3. I'm going to go right 3 and up 1. I'm going to take that horizontal asymptote of y equals 0. I'm going to bump it up 1. And I got y equals 1. And the resulting graph, if if you notice, is the same as the way we did it before. There's the same look, right, as what we did before. So our domain is still negative infinity, positive infinity. The range is still 1 to infinity. The horizontal asymptote is y equals 1, and so on. That's probably maybe a little easier way to go about this is to do it with the parent function 1/3 of the x, but it's not incorrect to do it the way I did prior to. All right, so I'm going to do this with the parent function being 2 to the x first, which has 0, 1, it has the point 1, 2, and so on, 2, 4, right? So how is this parent function being 2 to the x? Well, you got to rewrite this as 2 to the negative 1. That's 1 over 2 to the 1 to the x plus 3. In order to see that, multiply negative x. And now you want to think about it. Number one, let's do a reflection about the x-axis. Okay, let's do that first. So now, still have y equals 0. Actually, I'm not going to write that. I'm going to just flip it over. So instead of 0, 1, I got 0, negative 1. Instead of 1, 2, I got 1, negative 2. Instead of 2, 4, I got 2, negative 4. So here's the first transformation reflected about the x-axis. Now, number 2, let's flip it about, number 2, reflect it about the y-axis. So now, instead of 0, 1 stays there, but 1, negative 2 will become negative 1, 2. 2, 4 will be negative 2, negative 4, because we're flipping it about the y-axis. So here it is in green. Now, that's the second transformation. And finally, our last one, we just take it all and we, number 3, we bump it up 3, vertical shift up 3. So instead of the horizontal asymptote be y equals 0, now I'm bumping y equals 0 up 3. Up 3. And the entire green graph has to go up 3. So I'm going to take the point 0, negative 1, I'm going to bump it up 3. I'm going to pick the point negative 1, negative 2, I'm going to bump it up 3. I'm going to pick that point, what was it, negative 2, negative 4, I'm going to bump it up 3. And again, everything's the same as the green except we bumped it up 3. And if you want to plot some points, you could plot some points if you chose to, right? Like, for example, if you threw a 0 in to the original, I'd have negative 1/2 to the 0 plus 3. Anything to the 0 is 1, so I have negative 1 plus 3 or 2. So there's that point 0, 2 right there. Anyways, you can plug some more in. Your domain is still negative infinity, positive infinity. Your range is still coming from negative infinity up to that horizontal asymptote. Well, the horizontal asymptote became y equals 3 was our horizontal asymptote. So negative infinity up to 3, right? Range is coming up to that 3. And let's also take a look at this with our Desmos. Take a nice clean look at this. So our original function we said was 2 to the x. There it is in red. And so if you flip that about the x-axis, you'd have negative 2 to the x. There's the one. There it is in blue. And then we're going to take it and we're going to take that one and we're going to flip it about the y-axis. So there it is in green. Hey, that's nice. I think ours was also in green when we flipped it about the y-axis. And then we're going to take that one in green and we're going to bump it up 3. And there it is in purple. Right, there's our last one in purple. And maybe you can see that that y equals 3 in black is our horizontal asymptote of that one in purple, right? So there's kind of the transformations on that. The other approach to this problem is to make 1/2 to the x your parent function, which is this one. That's 1/2 to the x. And then you put a negative in front of that, which will reflect it about the x-axis. And you take that whole thing and you bump it up 3. And notice that green one is the exact same as that purple one before. So you can have your parent function be 1/2 to the x as well if you want to do it that way. So either of those would be great. All right, when we introduce solving exponential equations, what we do initially is we try to get them to have the same bases. So let's look at this first one, 4 to the x minus 2. This is a base 4. And so I'm thinking to myself, can I write 64 as 4 to the something? And hopefully you think, well, 4 to the 1's 4. That's not it. 4 squared is 16. 4 to the third. Oh, 4 times 4 times 4. That's what it is. 4 to the third is 64. Well, since they have the same bases, x minus 2 has to be equal to 3. And I solve for x. I add 2 to both sides, so x must be 5. And that's our answer. In other words, this is saying, right, like if you were checking it, does x equal 5 make this true? Well, sure, because 5 minus 2 is 64, and 4 to the third is 64. Sure enough, it does work, right? Let's do this next one, 1/2 to the 1 minus x. Well, I don't really like 1/2 because I'm thinking to myself, I can write 4 as 2 squared. So what about 1/2? Well, 1/2 is 2 to the negative 1. That's 1 over 2. So 2 to the negative 1 is being multiplied by that 1 minus x. So I got 2 to the negative 1 plus x, or 2 to the x minus 1. And now I'm like, oh, they got the same base. There we go. X minus 1's got to equal 2. Add 1 to both sides. X has got to be 3. And you can plug that back into the original, make sure it works. 27 and 9. So hopefully you're thinking to yourself, well, 27, I can make that a base 3. I can make 9 as 3. 9 as 3 squared. 27 is 3 to the third. So now let's multiply. So I got 3 to the 3x plus 2. Over here I got 3 to the 2 times 2x, 4x. So I got 3 to the 3x plus 6 equals 3 to the 4x. So I'm like, oh, exponents got to be the same. 3x plus 6 got to equal 4x. Solve for x. Looks like my x must be 6 for this one. Here I got 3 to the 4y minus 1 equals the square root of 3. So 3 to the 4y minus 1. Well, if you remember square root of 3, that's the same as 3 to the 1/2. So you have 4 minus 1. 4y minus 1 has to equal 1/2. Let's add 1 to both sides. So 1 plus 1/2, or 2 over 2 plus 1 over 2 is 3 over 2. And then let's divide this side by 4. So you've got y equals 3/8 would be your answer on that one. All right, how about e to the 3x plus 5 equals 1? Well, probably the only way to really think about this is to think, well, how do I get 1 as a base e? Well, anything to the 0 is 1. So we know e to the 0 is 1. And then we can say, oh, 3x plus 5 gotta equal 0. Subtract 5 on both sides. Divide by 3 on both sides. So it looks like negative 5/3 would make that work for us, right? About this one, we got 2 to the x minus 2 equals 8. Well, if you think about 8, you can write that 2 to the 1's 2, 2 squared 4, 2 to the third, there we go, 2 to the third is 8. So now we have 2 to the x times x minus 2 equals 2 to the third. In other words, 2 to the x squared minus 2x equals 2 to the third. So x squared minus 2x has got to equal 3. So we're actually solving an exponential now. And so I got to get one side equals 0. And so I'm going to go ahead and factor that. So x equals 3, x equals -1. Now we go ahead and test both of those and make sure they both work. And they do. Right? Let's do one last example here. Let's determine from a given graph what the exponential is. So if you look at this, I would notice I have this point 1 comma 7, right? I also, it looks like I have the point 2 comma 49. So I'm trying to write the equation for this. You know, what's the exponential? What would my a to the x be, right? And so I say, well, gosh, if I throw 1 in for x and 7 in for y, or let's do the other point, 49. Let's use 49 for the y and 2 for the x. You know, what's the a value that makes that true? And hopefully you say, oh, a's got to be 7. Right, 7 squared is 49. 7 to the 1 is 7, so on, right? So y equals 7 to the x would be one way to find that, right? And we know it's also increasing, so this base is going to be bigger than 1, right? But that's it for this section. Thanks so much for watching. See you next time.